Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, count number of beautiful subarrays. The problem states that you are given a integer array nums and you can perform the following operation on this array. The operation is you will choose two different integers I and j and a non-negative integer k such that kth bit is set in both numsci and numsj, and then you will subtract 2 to the power k from numsci and numsj, right? So what this operation is all about, we will select two indices and we will subtract 2 to the power k if kth bit is set. So what we are saying is we will just unset that bit. So select two indices, select any bit which is set in both the indices and you can unset them, right? So that's what the operation is. Now a subarray is beautiful if it is possible to make all of its element equals to 0 after applying this operation any number of times, and we need to return the number of beautiful subarrays in the given array, right? Now let's take an example. Let's say this is the array 43124, and now we are taking the subarray 312. Now if you look at it, let's say this is I and this is j, right? The binary representation of 3 is 1 1 and binary representation of 2 is 1 0. So the first bit is set in both 3 and 2. So we can just unset that, right? That's what the operation says. So if we unset the first bit, this 3 would become 1 and this 2 would become 0. Now we can apply the same operation on this. So here I is 0 and j is 1. So if we apply the same operation here, both the bit, the k equal to 0th bit would be unset in both of them. So this would become 0 0 0. So we are able to convert 312 to 0 0 0. And because we are able to do so, this subarray 312 is a beautiful subarray. Similarly, you can apply the same sequence of operations in the entire array 43124. Then you will see, okay, this is also a valid or a beautiful subarray. As there are only two subarray which are beautiful, the answer here is 2, right? So how to solve this? So notice there are various moving pieces in the problem. So first of all, you are given an array, you have to select a subarray. Let's say this is like you are given a long array, you selected this subarray. Now inside this subarray you have to apply the operations. Now for applying the operations, you have to first select two indexes I and j, right? And then you have to select an integer k which is set in both I and j, and you have to unset them, right? So lot of moving pieces. So firstly, let's try to reduce the problem. And the simplest reduction, as always in any bit problem, we have solved various problem in this way. I will attach the playlist in the description or in the I section in the top right below. You can watch that. Basically every time we try to solve the problem for a single bit first and then extend the solution to multiple bits. So in this case, let's reduce the problem and say we have only single bit, right? And because there can be only single bit, the array would contain either 0 or 1. So here we say that okay, k is always 0, right? Because there is only single bit. So we are saying k is always 0. And our array would look something like this. So we'll say okay, this is our array which contains only single bit, and because this is only single bit, each element can be either 0 or 1, right? Now let's try to solve the same, find the number of beautiful subarray in this reduced problem first, right? Now how to solve this? Again, you have to select a subarray first, right? So let's say you selected this subarray, for example, right? Now we have to make everything as 0. So let's say this is, you selected this is as I and this as j, right? And you have to make everything 0. Now there is only one bit, right? And that bit is set here in both the cases. So you can unset them. So you will convert this to 0 0, right? Now there's one left, and there is no operation you can apply to make this 1 0, and hence this subarray is not a beautiful subarray or a good subarray, right? Now let's take one more example. Let's say the subarray is we are taking care of is this. Like this is the subarray we are considering. Now here again, like there are four ones, right? And we need to convert everything to 0. Let's just pair the first and second, right? and this both will become 0, right? And similarly you can take this as again ing and make them 0. So basically we are able to convert everything to 0, and hence this subarray is a beautiful subarray. So notice what's happening. Previously we don't like we will not able to pair all the ones, and that's where the previous array was not a beautiful array. But in this array we are able to pair all the ones, and hence this array is a beautiful array. So what's the observation? The observation is, if the array contains even number of ones, then only the array is a beautiful subarray. Otherwise, that subarray is not a beautiful subarray, right? So the problem is now reduced to finding how many subarrays are there which have even number of ones, or in other words, how many subarrays are there which have even sum. So we are now solving this problem. Count how many subarrays are there which have even sum. So this is a very standard problem. I would strongly encourage you to pause the video right away and try to solve it yourself first. So, okay, hope you thought about it. Now, how to solve this? Notice, like the easiest way to solve this is through this algorithm. We'll say, okay, we'll iterate over all subarray. So let's say this is R, right? So we'll iterate over all subarray in the sense that we will try every possible L for this R, right? And for each L and R pair, we will find the sum and then see if sum is even or not. If it is even, we will just increment our result, and finally this result would contain the number of subarray which have even sum, right? Now this works. What's the complexity? Complexity here is order n for this loop, order n for this loop, and this loop can go up to order n because you are calculating sum. So this you can easily convert this order n to order 1 by doing a prefix sum, like by maintaining a prefix sum. So let's do that. Let's say you maintain the prefix sum, and prefix sum looks something like this, right? So uh, now this is the prefix sum, right? And uh, we will remove this, like we can do this entire thing in order 1. So the complexity is order n square, right? Now this order n square is not good enough. Why? Because remember we are trying to solve the reduced version first, and in the original version itself we are not allowed to do order n square. So that's where this order n square would not work. We have to do something better, right? What exactly we will do? First of all, order n square doesn't work. What does this mean? It means that we are not allowed to iterate over all the else, right? So this is something we have to avoid. Now this loop is something we want to ignore from here, and that's what our goal is, right? Now let's talk about what is the sum. Sum is prefix of r minus prefix of l, right? So that's what the sum is every time, right? And what's the goal? The goal is we want the sum to be even, right? So we want this to be even always. So let's think about it. So difference of two integers. When difference of two integers are even, so we already know r, right? So in other words, we already know prefix of r. So prefix of r is 3, right? And you have to subtract something from here such that it would become even. So every such indexes are a valid index which can give me a even number. Now subtracting two number can give even number only in two cases. So odd minus odd is even, and even minus even is even. So we can, if p of r is odd, we want p of l to be odd. If p of r is even, we want p of l to be even. That's the only way to get a even integer by subtracting two integers, right? So that's what our goal is. What we will do, we will say, okay, we know prefix of r. Now if prefix of r is even or odd, we'll just, let's say the prefix of r is odd here. So we'll say, okay, count how many odd indexes are there. So there are two odd indexes here, right? And hence we know that, okay, we don't need to iterate over all the else. We know there are two possible else here. So we'll just simply do result plus equals 2, right? And that way we will be able to avoid iterating over all the L, and this order n square would become order n, right? So hope that makes sense. So what we are trying to say is somehow we need to count the number of odd indexes before and number of even indexes before. So that's it, very simple, right? Now one way to do this is just convert everything to 1 and 0 again. So what we'll say, okay, if it is if it is odd, we will denote it with 1. If it is even, we will denote it with 0, right? So here you can see 2 is even, so that's why it is 0. 4 is even, 0. 4 is even, 0. 6 is even, 0. And 6 is even, 0, right? So every even we denote by 0, every odd we denote by 1. Now for this, what we need to do, we need to just found out number of ones before this, right? Basically we want number of odds before this, and odd is 1, right? So that's why we need to find out number of ones before it. Similarly, let's say this is the r. So because this is 0, we need to count number of zeros before it. That's the simple approach, right? So hope this makes sense. So what we are now, the problem is for every index we just need to find out how many instances of that particular value occurs in the left. If it is 1, count number of ones. If it is 0, count number of zeros. So the pseudocode for that would look something like this. uh, we will first make everything to 0 and 1, right, for simplicity, and after that we will just maintain a map and increment our result with the frequency of current element. So basically the frequency of current element would denotes how many such elements exist in the previous indexes before to r, right? So basically for this particular instance, prefix of r would contain how many, or prefix of 1 would contain how many ones are there in the prefix. So every time we enter into this loop, we are also incrementing the prefix of current index. So at this, when we cross this, we'll add 1 to the one key of this map, right? So this entire solution would work in order n, right? Because we are just iterating once over the entire array and maintaining and doing some constant operation here. So this map can be reduced with unordered map, it is if it is C++. So this entire algorithm would run in order n, right? So just to reiterate what we have done, we have to find the number of beautiful subarrays in a array which only contains single bit. That is, every element is 0 and 1. So we did some observation and we found out that, okay, for subarray is only good if we are able to pair all the ones. And to pair all the ones, it means the array should contain even number of ones. And because of that constraint, we can say that, okay, the problem is exactly similar to number of subarray with even sum, right? So for this we maintained a prefix sum, right? And what we are saying is we know prefix of r, right? And we want prefix of r minus prefix of l to be even because that's the sum, right? And if prefix of r is odd, we want prefix of l to be odd. If it is even, we want prefix of l to be even, right? That's where we converted everything here to 0 and 1, where 0 denotes even, 1 denotes odd. Now, if prefix of r is 1, it means we need to count out number of ones in the prefix. If prefix of r is 0, we need to count out number of zeros in the prefix. So for that, we have this pseudocode and the entire algorithm would run in order n, right? Now, this entire thing was for the reduced version. So let's go back to the original version of the problem where we have more than one bits, right? So let's say this is the array 43124, right? Now you convert this array into a into their bit representation. So this is like the bit representation of 4001, right? Similarly, this is the bit representation of 3110, right? And so on and so forth. So you converted the array into bit representations, right? Now you want to understand whether a subarray is good or not. So let's say you are talking here, so you are talking about this subarray or 312, right? So you need to find out whether it is good or not. Again, you can apply the same exact trick with every bit. So you want everything to be zero, right? Everything would be zero if once every bit would be zero, right? So you want this to be zero. So basically you can simply say I can pair this to one in this bit. So this entire bit is good. Like we can convert everything to zero. Similarly, I can pair this to one in this particular bit. So this entire bit is also like good because we can convert everything to zero here, and this is already zero. So basically we are able to pair every bit and we are able to make them zero, and hence we can say this entire subarray is a good subarray. So notice that this is exactly similar to the one dimensional view. Here we are just saying that the same is true, same should be true for all the bits. That's the additional thing that we are trying here. So what we will do, we'll apply the same algorithm. We found the prefix sum, right? So we just calculate the prefix sum. Now with prefix sum we will simply convert this prefix sum to 1 and 0 because we have done the similar thing in the previous part. So now this 0, this one, or let's say this one denotes that, okay, there, like this prefix sum at this index is odd, right? And this 0 denotes that prefix sum at this index is 0, right? So once you have done this, what you can simply say, okay, for this r, for this r, only else which contain exact same configuration would be good, right? So basically for this bit you want 0, for this bit you want 0, and for this bit you want 1, right? So that's what you want. So basically you will say, okay, only only indexes or only L, this is R, right? So only L which have exact same configuration would would form a good subarray or a beautiful subarray, right? So similarly for this you can see there is a 0 0 0. So this will also form a good subarray, right? So hope this makes sense. So what we have just done, we have solved single dimension of the problem first, and we are saying that the same should be true for all the dimensions, right? Now for this dimension, like we after converting this to prefix sum, we are saying that for this dimension we want this to be 0, like only indexes, let's say this is R, so only index which have 0 here are good. So for this bit all of these indexes are good, right? Now for this bit only index which contains 0, so this index is good, this is not good, so this is now gone because you want everything to be satisfied, right? So this is not good, this is good, so this is okay, this is also good, this is okay. Now for this bit also you want everything to be 0, so again this is 1, so this is now gone, this is 1, this is again gone, and this is 0, so this is okay. So finally you want everything to be exact same configuration, and you can simply do that by maintaining a map, a 2D map here, right? So I would strongly encourage you to code this solution yourself. That would give you a bit more clarity. So let's look at the code. The code is very straightforward. We have simply calculated the prefix sum here, right? And after calculating prefix sum, we also make it 0 and 1 based on whether it is even or odd, right? So we simply take it modulus 2, that would convert it to 0 and 1. Now after we have done this, we simply maintain a map of frequencies, and this is exact same algorithm that we have applied for one dimensional array, right? So hope this entire solution makes sense. If you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.